Okay, 8.11, we're finding volume with the washer method, and we're going to revolve around the x or y axis. Okay, let's consider this situation first. Okay, I'm going to look at the area bounded by these two functions. Let's look just at this part right here. Okay, now I'm going to imagine I'm rotating it around the x-axis for no particular reason other than we did the example in terms of x. Okay, so if I'm rotating this around the x-axis, it's kind of like there's this thing here. Okay, and now if I do the rotation right here, it just looks like a circle, which is kind of like what we've been doing this whole time. Except for the circle's actually not filled in because it's only this little piece that's getting rotated. It's not the part in the middle. If I go to a middle part of this surface, like say I go here, I have this rotation out here, and then I kind of have this rotation on the inside. So the part that's actually the new solid that's being created is looks kind of like this. Okay, because of that, it kind of looks like an outside circle with the inside circle cut off, which looks like a washer, like with a screw, like hardware. Okay, this is why it's called the washer method. Okay, so all of these little cross sections are going to be shaped like this, a circle with a circle cut out. They look like washers. So if you want to find the volume of this solid that's created with the revolutions, you want to find the area of the circle on the outside and then subtract the area of the inner circle. And each of those areas depend on the radius, and the radius depends on which function's on the outside. So for our particular example right here, that bigger radius is going up from here, from the x-axis to here. And I'm going to call that big R of x because it's going to be the bigger radius. And then this inner circle is by the lower function, which is we're going to call it little r of x to indicate it's smaller. So if I want the volume of the solid of revolution, I'm going to do the volume created by the outer circle, like if this were all solid, which is going to be pi big R of x squared dx, and I'm subtracting the volume of this little inner piece, which is pi little r of x squared, or you can factor out the pi and we do big R of x squared minus little r of x squared. Okay, let's try it for real now. Example 1 is actually the same picture we're looking at. So it's the volume enclosed by y equals root x. This is root x, and y equals x squared. Okay, we're going to rotate it about the x-axis, so I'm taking just this enclosed region and I'm rotating it about the x-axis. Hold on, let me redraw my line straight. Okay, I'm rotating it around here. So this piece is going like this. Okay, and then just imagine it's rotating around. It looks kind of like I don't know, a hollowed out tulip. Actually, tulips are hollow, aren't they? I don't know. Okay, let's find that. Okay, I'm going around the x-axis, so I'm doing this in terms of x. The x looks like it's going from 0 to 1. If I wasn't sure, I could set them equal to each other and solve. Okay, now I want the area of the outer circle minus the area of the inner circle. So let me see which one is the outer circle. Okay, the bigger radius is the farther distance, so it's going to be from the x-axis all the way up to this line, which is the root x. So let me do pi. Okay, the bigger radius is the root x. Okay, I'm going to go ahead and square that and then keep the pi on the outside, minus. The smaller radius is created with this function, which is the x squared, and that's the distance from here to here. And I'm squaring that because it's the radius squared. Okay, and I'm doing this with respect to x, so I'm going to put dx. Okay, so let's think about this. This is really saying pi big R squared minus pi times little r squared, except for I didn't write x squared squared. Okay, and that should give me, and once I integrate it, it'll give me the volume of the rotated solid. Okay, let's go ahead and simplify this because we're going to calculate it, and it's not a calculator active problem. Okay, I'm going to put the pi on the outside for no particular reason other than to put it out of the way. Okay, pi x squared is just going to be x. X squared squared is x to the 4th. dx. Okay, let me go ahead and do the antiderivative. That's x squared over 2 minus x to the 5th over 5. I'm going to evaluate from 0 to 1. So 1/2 minus 1/5 minus 0. Okay, 1/2 minus 1/5 is 5/10 minus 2/10, so that's going to be 3/10 pi. They didn't tell me the units, so we'll just call it cubic units. Okay, let's try another one. Okay, find the volume if the region enclosed by y equals x squared plus 1 and y equals 2x plus 1 is rotated about the y-axis. Okay, where's the y? This is the y-axis. Okay, the enclosed region is this thing right here. Okay, and I'm rotating it about the y-axis, so it's going to go around like this. And you don't really have to picture it, you just have to know which direction it's going in, but it's going to go, let's see, something like this, and then the inner function. And then there's like an inner function that goes like this. So it's still making little washers, so to speak. Okay, I'm going along the y-axis since I'm rotating around the y-axis, so let's do this in terms of y. Okay, in the y direction, okay, the lowest y value is 1. Okay, and then it looks like it's going up to y equals 5. Now, if I was not sure, I could always solve it. Let me solve it off to the side. X squared plus 2x plus 1, x squared minus 2x equals 0. Okay, I got x equals 0 and x equals 2, but I actually want the y values, so I need to plug the 0 and 2 into either one of these functions. It wouldn't make a difference. So it'd be y equals 0 squared plus 1 is 1. Y equals 2 squared plus 1, that's 5. So it is 1 and 5. Okay, but if you can tell from the graph, that's okay too. Okay, now I want to do the area, so this is going to be pi. Since it's a washer, I'm going to do the outer radius squared minus the inner radius squared. So from the y-axis to the outer radius is taking me to the y equals x squared plus 1 line. But I'm doing this in terms of y, so I need to solve this. So x squared equals y minus 1, x equals, now it's either plus or minus y minus 1. Okay, let me look over here. Okay, so if x is plus or minus, well, x is positive on this side and it's negative on this side. So we're going to go with the positive version. Although technically we're squaring it in a second, so it's really not going to make a difference at all. But it makes a difference in some of our other applications, so I'm going to keep doing it. Okay, so that's the bigger radius. Subtract. The smaller radius is going from here to here, and that is my line. Okay, but I'm doing this in terms of y, so let me solve it real quick. Okay, so that's going to be my inner radius. And then this is all done with respect to y. Okay, let's go ahead and simplify this a bit. Square root of y minus 1 squared is y minus 1. Okay, I'm okay with that. Okay, and then I think I'm going to turn this into a calculator active problem, so hold on. Calc? Yes, let's use our calculator, because I don't want to simplify that. Although I could. Okay, go ahead and put that expression in your calculator. If we do it out for exact answer, we would get 8/3 pi. If we do an approximation, we get 8.3776, and these are both cubic units.